Hello and welcome back. I thought we would try something a little different today. So normally I do advent of code problems, but there is this site called Rosalind, which I had this zoomed in, hopefully, so that people on smaller screens will be able to view it. But I guess we'll see. Anywho, Rosalind does programming problems related to bioinformatics. I don't really know that much about bioinformatics beyond like high school biology. But the cool thing about it is that just like Advent of Code, they give you a problem, they give you a data set. You're free to use whatever programming language you want to compute the answer, and then you submit the answer. So there's no server side running of code going on here. And that means that we are free to use APL to solve these. Um, yeah, I figured we'd take some time, solve a few of these, see how it goes. I solved some problems on this site several years ago, I think in 2020, but I forgot my account details. So we're starting from a fresh account here. I think the way that this works is if we go to the tree view, yeah, these nodes are kind of small. You can sort of see that as you solve problems, you basically unlock additional problems. So we'll be starting at the top of the tree. I kind of prefer the list view. Yeah, we'll just go through, solve some of these, and I'll give an explanation of how to go about solving these things. Okay, so the way these problems work is basically there's like some text about you know like some background about bioinformatics and genetics and all this good stuff. You're free to read this on your own time, but I think the meat of the actual problem statement is here in the problem section. So let's see. So we have a DNA string, which the alphabet consists of the letters A, C, G, and T. And they're going to give us a DNA string, and we give back 4 integers counting the number of times the symbols A, C, G, and T occur within that string. Okay, fair enough. So let's copy this example data set here, and we can attempt to solve it. So we'll just assign this string to P. This problem sort of seems like kind of a classic outer product problem. So the way I might solve this at first glance is I take the alphabet of characters that we're interested in, and then I do like outer product equals on P, and that gives us a Boolean matrix where each one of the rows represents one of these letters, and a 1 occurs where the letter in P is equal to the letter on the left, and then if we just sum the rows plus reduce, we get an integer vector representing how many occurrences each one of the letters has. So 20, 12, 17, 21. Yeah, that seems correct. You might be tempted. So one other way that you might do this is to use the key operator. So you could do like key concatenate jot length here, I think, yep. And then we can sort this on the rows like so to put everything in order, and then we can just take the rightmost column. But so key operator is useful certainly, but the trick is basically, so like if you do this on a string like CCGGTT where there are no A's in it, then you only get a 3-element vector because there are no A's in it, and it doesn't, like the key operator isn't aware of that, and it's not going to insert a 0 there. So when you sort of like know, like when you know a set of things and you want to count those occurrences, I think outer product is oftentimes going to be the simplest way to do it. On very large data sets, you might want to try something else because it's not super efficient and you have to like materialize this giant matrix. But I think for the data sets that we're talking about here, it's going to be fine. So let's see. Yeah, the way this works is you download a data set. I did sort of a test download before and timed out, but you download the data set and then you'll have 5 minutes to upload the answer. So I think what I'm going to do for this video is just, we can make a file and we can start storing some solutions here. The problems have 3-letter identifiers, so this is DNA, and we'll say inget. All the text files have this sort of like format. So we'll say like this. So it's Rosalind underscore and then the 3-letter identifier for the problem. This is P, and then we just do this, and this will give us our vector. Okay, great. So that should work, I'm fairly certain. So let's download the data set. Try again, maybe. Okay, Rosalind underscore DNA.txt. So now I can just copy these lines here. And I get, oh, that's interesting. What does P look like? Oh yeah, I need the first line here. That's right. And I get this vector, which we can just copy paste and put here. For some like very large answers, we may have to write them to a file later, and you can actually upload a file. So let's see. Okay, great. Yep, we solved a problem. Oh, cool. Now we can go to, oh, this interface doesn't do well with being this zoomed in. So we can go back to the list view and see what new problems we've unlocked. Oh, one other thing that I'm going to do, I'm just going to do like utils. This alphabet, this ACGT, I'm pretty sure we're going to end up using quite a bit. So I'll just assign this to BP for, I think these are called base pairs. I'm not really sure. But yeah, we can do BP there. And oh, this needs to have a second disclose. And if we just, oh, but you don't know what BP is, so we'll copy the whole thing. And yeah, we still get our answer. Okay, cool. So that's the first problem. That's DNA. What else do we got? Transcribing DNA into RNA. An RNA string is formed from the alphabet A, C, G, and U. And we take a DNA string, which I guess has A, C, G, and T, and we replace all the T's with U's. So, okay, we'll take our sample data set here. We'll call this P, and there's a couple different ways to do this. So one way you could do it is you could use the at operator, and you can give it a function. You can give it a function that results in a Boolean matrix. So we could do this on P, and at every location of a T, we can instead have a U, and that works. But I think a better sort of like more general way to do this is we can say, so we have BP, which is ACGT, and we can say BP index of P, which gives us this, and then we can index into it using ACGU instead. And this allows us to do, you know, if you have to do like other replacements, you have to like start chaining the the at symbol, and this is sort of like a more generalized way to do it. So you can use whatever alphabet you want here instead. Maybe we use the RNA alphabet again, so I'll call this like BR for base RNA. I don't know, naming things is hard. And the code for this one is, yep, it's RNA. So again, it's going to be a single string. So we'll just write RNA here, and this will be, let's see, so this will be BR index BP index of P, right? And then, so, and just to make sure, like this answer seems, the sample answer seems like the sample output, I'm pretty sure, yeah. Okay, cool. So we have our utils and everything in memory. We're good to go. This should theoretically work. So we'll download the data set. And doesn't want to give it to us. Rosalind RNA.txt. So we can just copy this and paste it. And we get a fairly long line here. Yeah, so copy that. Paste the answer here. That's quite a few characters, yeah. There's some limit on the buffer when you're talking about output. So yeah, I think eventually we're going to run into this thing where we have to output it to a file and upload it, but we'll see if this got truncated or not. Nope, seems like that worked. Okay, let's go back to the list view. Complementing a strand of DNA. Again, we have a bunch of like, if you want a course in genetics and bioinformatics, you can read the flavor text, but much like advent of code, I skip a lot of the flavor text. So symbols A and T are complements of each other, and as are C and G. And the reverse complement of a DNA string is the string formed by reversing the symbol of S, so reversing the string, and then taking the complement of each symbol. Okay, so we'll take this sample, and this will become P. So the idea is first we reverse P, and then just like before, I think basically we have to do some replacements. So we do, first we find out the indices, and then A and T are complements of each other. So T, so are C and G. So G, C, A. Oh, I guess it's just, hang on. This is just the base pair is reversed, right? A, C, C, G, G, T, is that right? Yes, it is. Okay, cool. So, reverse complement, Rev C is apparently the code name here. This is again going to be a Rev C. This is going to be a single string Rev C, and then we just do this. If you are allergic to angle brackets, by the way, which I sort of am, then you can also use the index function complement enclose like this. That works too, but it is one more character. So I like to save, I like short answers. So I'll use the angle bracket notation here. Yeah, this should be good for Rev C then, pretty sure. We'll download the data set. Rosalind Rev C is now on disk. And we can have a very long string. Let's see if that works. Yep. Okay. Back to list view. Rabbits and recurrence relations. Oh, geez. Okay, what are we? Fibonacci sequence. Yep, got it. So this is 1, 1, 2, 3, 5, 8. Rabbits reach reproductive age after 1 month. And you begin with newborn rabbits, so they take 1 month to reach reproductive age. And then any given month, every rabbit of reproductive age mates with another rabbit of reproductive age. Okay. Rabbits never die or stop reproducing. So we could just calculate the Fibonacci sequence here, but the problem is that they produce k rabbit pairs instead of only one pair. In months, so the first number is in, and the second number is how many rabbit pairs they produce. Okay, fair enough. So we have two numbers, and these are n and k. And so there's probably like a mathy way to do this. What I'm thinking of doing though is just like doing a simulation. So basically we have two categories of rabbits. We have rabbits that are newborns and we have rabbits that are reproductive age. And basically every month all of the rabbits that are reproductive age produce 3 more rabbits, and all of the newborn rabbits become reproductive age. So we can start like basically we can have a vector. So we start with one newborn rabbit. I'm pretty sure if we begin with one pair, each generation, yeah, okay. So we can just have a vector where like the first number represents rabbits, like newborn rabbits, and then the second vector represents, or the second number in the vector represents our reproductive age rabbits. And so the number of reproductive age rabbits that we have is just going to be the sum of our vector, right? Because reproductive age rabbits never die, so they are still reproductive rabbits, and then we're just adding the number of newborn rabbits. And then the first element is going to be 1 drop W, so the second element, multiplied by K, right? So that's, and then we can just use the power operator. So we can run it like 2 times. So on the first iteration, our newborn rabbit becomes an adult rabbit, and then we get 3 more adult rabbits, and yep, and then I would expect this to be like 12, 7? Yeah, okay, cool. And the question is basically, after n months, how many rabbits do we have? So for our sample data set, the output is 19. So it looks like if we run this for n minus 1 times, we get 1217, and then we can just add those to get 19. Yeah, this is probably fine. This can be a train, I guess, if we want to save a character. So you can do this, and then this is right tech. Yeah, okay, cool. So what's the code for this one? This is fib. So we are looking at fib, and we are again getting a single string, but rather than assigning it to p, we assign them to nk now. And for a second line, we do this. Yeah, I'm pretty sure that should work. Like I said, there's probably some mathy way to do this, some like analytic method, but I think this is fine. So we can download the data sets. We now have Rosalind fib. Oh, okay. Well, what do we got? 30 and 4. What's the shape of this? Oh, these are integers. I need to parse these. Okay, well, fair enough. So, this is a classic advent of code thing, but we can say does not equal partition like this, and then we say for each execute, and we get numbers. And then this can be nk. And then we run this thing, and we get some very large number. If we set the print precision higher, hopefully we can get the actual number. There we go. And hopefully this works. I was on the clock for that integer parsing. Great, yeah, this seems like it worked. So let's change. We are parsing here. And if we get another integer parsing problem, I'll probably break this function out into our utils section above. And let's just make sure. So I had to set pp to 34. Okay, cool. That is Fibonacci with rabbits, I guess. Okay, what else we got? Computing GC content. The GC content of a DNA string is given by the percentage of symbols in the string that are C or G. So we get a bunch of strings in FOSTA format of length at most 1,000. And we need to return the ID of the string having the highest GC content followed by the GC content of that string. Okay, so this is our sample data set. This will show these. So in each section, I wonder um, in the actual problem output, I wonder if these will be single strings or if you're meant to concatenate everything between the identifiers. Because, so like if we create a test file and we insert like this, you can see that these are going to be separate lines. So I'm not sure what the actual problem input is, but it doesn't hurt to do the concatenation, I guess. Okay, cool. So we will inget our test inputs, and we got a bunch of nothing because I have to close this and save it. Okay. Right. Now, let me think. You know what? I actually bet that because they've given us really long strings before, so I'll bet that these are meant to be single strings. I don't want to do the concatenation unless I have to. So we'll save this to disk. Okay, and now the reason that this makes things quite a bit easier is because we can say, so if we look at the length and we divide this by 2, and then if we add 2, and then we can say right tech row commute, this will put it into a 2-column matrix where the left column has all the identifiers and the right column has all of our stuff. And then if I transpose it and I break this down, I can say, so we have identifiers and we have our strings. So we have identifiers and we have strings, right? Now, for each one of the strings, computing the GC content is not really that crazy. So we just want to say which one of these are in the set GC. And, this might actually, so it'll be sum, divide, yeah, this would be better as a function. So WNGC sum divide by length, right? And we get one of these numbers is supposed to be 60. Oh, so we do 100 times, and we get this 60.919 number. We can, so the problem is, what we'd really like to do is, so if we sort this, we get this. I wonder if I can train it. So, yeah, so let's say that I take the IDs and concatenate them with the table of this. right? And then if I sort this, I should be able to index. Indexing is going to be kind of a pain. Enclose jot, like so. Okay, yes, except that I want this to actually be descending. And then I can take the first element, and if I mix these, nope, because that's a number. So I can say for each format, and then mix, and this gives us a nice thing that we can just copy and paste. And Rosalind 808 60.91. Yeah. Okay, great. How gnarly is this? fairly gnarly. The actual calculation for the GC content is not that bad. The problem is that we have to somehow catenate the ID and pull that out as well. Yeah. So let's take this one out just because to make the train smaller and easier to read. Yeah, I mean, I think it's fine. So, okay, so this is GC. GC apparently. And then, so what did we do here? We did some parsing, like this. This is no longer going to be test.txt. This is going to be Rosalind underscore, wow, what was it? GC. And then the actual solution will look like this. Whoa, 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 whoa. Yeah, okay, so I can actually test run this whole thing on test.txt. And I appear to get the correct answer, so yeah, Rosalind underscore GC. So yeah, to find the GC content, we generate like a Boolean vector where we check whether it is in the set of GC, and then we add it up, we divide it by the total, or we take the total number of elements divided by that. That gives us a percentage, so we do 100 times, and then we do this thing where we like find the largest one, but we sort. We concatenate the IDs, so we sort both of those things at the same time, and then we do some formatting to make it easier to copy and paste. Okay, cool. What do we got? Oh, this is probably useful to know. Absolute error. I think, yeah, they must do some error bounding here because we have a higher degree of precision. So hopefully they don't expect exactly that number. Otherwise, I'm going to have to do either something with like print precision, or I'm going to have to do some numerical rounding. Rosalind GC is now on disk. This doesn't seem, oh, no way. They did do this. So I do have to cat rate these. Um, wow, well, that is annoying. Okay, we might time out this one then. So let's see. Rosalind gc.txt. In order to, let's see. So in order to get the, in order to get the, so if I take the first element for each one of these, and I say, because all the IDs start with this character, right? Does not equal, and then I feed that into the partition function, then I should get, yes. Oh no, that's not helpful. How about that one? Yeah, this is better. Right, and then for each one, we'll just do an in the list. And then if we look at the length of this, that gives us 10. So we'll say that this is S, or the strings, right? For the IDs, we'll call this P. For the IDs, we want sort of the same thing. We want each one first equals, and then we feed that into partition. Oh, no. Oh, I guess I can just, hang on, hold up. If that's a Boolean vector, then I can probably just filter it. Does filter work in trains? Do I need these? Pretty sure I do, yeah. Okay, so we'll call this I for IDs, and the length of I should equal the length of strings, and they sure do. So, okay, so I have I have S, and now I have to do this thing. This gets a little hectic when you're zoomed in this much. Anyway, I just want to see if we can do this before we time out. Let's give it a shot. Wrong answer. Okay, fair enough. Let's see what we've got so far. So we've stated that S looks like this. And then we have a separate line for calculating I, which is this one. Okay, now if we go back to our test input here, and we see this, and now we do the partitioning thing. If I run this on the test input, what do I get? Yeah, well, that seems to be, it's not a digit precision thing, is it? That would be super annoying. Rosalind allows for a default error of 0.001. Okay, so it's apparently not that. I guess that we are off in our calculation somehow, that we get to say, we get the answer for the test input. Yeah, well, let's look at our strings. So these strings, I guess, seem more or less correct. Well, it's a little bit difficult to tell. The IDs are correct. Oh, you don't want the... Okay. You don't want the little caret on the beginning when you're considering your ID. All right, well, fair enough. So for so this is how we're pulling out our identifiers, and then basically we're gonna do one drop on each of these, and that'll give us the raw identifiers. Let's solve the problem first, and then we can see about cleaning this up a little bit. Okay, so this is going to be Rosalind underscore GC. If I do this on my previous output, yeah, I mean, it's the same. It's the same answer. I just don't have the caret in front. So, okay, and let's remove the previous one. Okay, cool. So now when we download it, we won't have this extra thing. So let's download a data set. I'm pretty sure that the data sets change every time that you download them. So Rosalind GC is on disk, and we're gonna do this, and I don't think that these extra spaces should matter, but you're never too certain. Okay. Yeah, okay, so we solved it. What could we do better here? I guess we could so if we look at our, how long is this video already? Oh, 44 minutes. All right, I'll go for another 15, 20 minutes or so. So if we look at our test input, we could partition things so that, just like before, if we take the first element of each one, and then we look at equals, and then we feed that into the partition function, this will give us an ID followed by a series of strings, right? And we could just call this P. And then we do this thing with P. The only difference is that rather than this, we're going to do one drop. So we get rid of the identifier, we'll enlist everything, and then we'll do the checking for GC content. And I guess we can call this like R, and this is going to be length R, right? Yeah. Okay. Then we do 100 times. And now we can sort this, find the largest one, and we can use it to index into P, like so. Then we take the first one and the first one again. Oh, but we need the, we need the GC content number. Yeah, okay. I mean, I think this is probably fine. Yeah, this is fine. Okay, cool. Well, anyway, we'll move on to the next one. So the actual like GC content calculation is not hard at all. It's kind of the parsing and everything else. Counting point mutations. Given two strings S and T of equal length, the handing distance is the number of corresponding symbols that differ in S and T. Oh, well, okay. We will again boot up our test inputs. And this will just be inget test.txt1. We can just do not equal reduce and take this. And the question is the number of symbols. Yeah, 7. Okay. So this is what, ham? 2 M's? 2 M's. And there's no identifiers or anything, so I don't think they'll do the concatenation thing to us. Okay, ham is on disk. 468. Okay, kind of an easy one. Mendel's first law. Oh boy. Okay. So we get 3 positive integers representing a population containing organisms. Homozygous dominant, heterozygous, and homozygous recessive. Okay, yeah. I vaguely remember this stuff, again, from high school biology. Probability that 2 randomly selected mating organisms will produce an individual possessing a dominant allele. So I think the way this works is basically, yeah, so you have 2 organisms that have, they're either like they have like two, I don't know what you call them, genes or alleles, and then they can either be like dominant dominant, dominant recessive, or recessive recessive. And then when they pair, you sort of do like a, this is almost like an outer product type of deal where you randomly pick one of them, and then you randomly pick one of them, and yeah, you get four possible options from basically just like pairing them together. Okay, so all right. So I think, especially if we're just interested in dominant alleles, I think we can represent this stuff as like a Boolean vector, right? Where um, we say that the dominant trait is a 1, the recessive trait is a 0. Um, and then, so the order is homozygous, which will be homozygous dominant, which will be 1, 1. Heterozygous, which will be 1, 0. And then NMR homozygous recessive, which will be 0, 0, right? So we get, if we look at like our sample data set, and let's reduce this a little bit. So I think that like we can sort of build a matrix of our three possible options here. And if we mix these, there's probably a shorter way to do this, let me think. So if I do like iota 6, 3, 2, row, 3 greater than or equal to, yeah, shorter, always better. And then I can just do P, select first, or replicate first. Yeah, and so this will say, you know, the first number of P indicates how many 1, 1s we have. So those get replicated out, and then the second number is second row, third number is third row, etc. Okay, so these are sort of the gene mappings. I'm not sure what the terminology is, but these are sort of like yeah, these are our representations of our organisms, and we'll call this like R, I guess. And then the idea here, so the problem with just like, it would be really cool to just do like outer product catenate, I guess. No. Okay, wait. So let's say that we're operating on individual organisms. So we do rank 1 some function. So we're operating on rows here. And the problem is basically that you don't want to, the problem is that you don't want an organism to mate with itself, right? And so you want it to, oh, and let me back up. So my approach with problems like this, again, there's probably like mathy ways to do it, but basically I just kind of like simulate the entire universe, the entire universe of possibilities. And then we can just look at those. And especially because we're looking at the probability that 2 randomly selected mating organisms will produce an individual possessing a dominant allele. We'll just simulate all possible pairings, see which one of those have a dominant allele, and then we can divide one by the other, and that'll give us our probability. So, okay, so rank 1, we're operating on each individual organism, but we don't want them to mate with themselves. So what we could do is we could do like R index of the row. Yep, and then we could do iota length R does not equal. Yes, and then we can, this is a Boolean vector that we can use to filter R. Yeah, so each one of our organisms, if we look at the shape of this, Yeah, so we have six possible organisms. Each one of them, not counting themselves, has five possible mates, and then we have the two for their we have the two for uh, their alleles. So, and then what do we do? So we have a filtered result set. I think we do catenate rank 1 with W maybe? And then if we mix this and look at the shape of it, yeah, this looks correct. Right, okay, so the way that and we're dealing with like 5-dimensional arrays right now, which can be a little intimidating, but you just have to remember that each one of the axes like actually signifies something. So we start with 6 possible organisms. They have 5 possible mates, not counting themselves. We have two possible alleles to pick from the first one. We have 2 possible alleles to pick from the second one, and that gives us a string with 2 alleles. So we can do an OR reduce now to see which one of those have which one of those offspring have at least one dominant allele. And this gives me some, I have to do a mix here, right? And I'm pretty sure that we can just enlist this. And what's the length of this? So we have 120 possible offspring. And the idea is that if we look at the sum divided by the length, we get 0.7833 repeating, which is correct. I actually think, hang on, so I think that you can just do, since we're doing an OR reduce anyway, I'm pretty sure that we can just do OR in our outer product here, right? And if I look at the shape of this, yeah. So, and then we can just do this part. So because we're doing the OR reduce later, we don't really have a reason to do the catenation. We can just do this. Okay, this works. Man, it would be really cool though. Hang on, getting a brain blast. All right, so it would be cool if we could do like outer product OR here on R. The problem is that if we look at the shape of it, we have organisms that are mating with themselves, which is bad. So we could do some filtering. What if we did? So if we did like iota length R, we get this. And we could do an identity, well, an inverse identity matrix like this. And then because we're talking about 2 alleles, we can replicate each row, right? And then, so we have that. We have, oh, hang on, give me this thing. So what if we have this and we use this to filter rank 1, 2. Oh, it gives me a rank error. What's the shape of this? 12. So there should be, I mean, there should be 12 matrices if I do 6 times 2. That's unfortunate. Is that, I still get a rank error. Hmm. Well, this is too bad because I want to use these like it would be cool to use these Boolean vectors to like filter each one of the matrices, and I think this is the right size for it. I'm not immediately sure why this doesn't work. Okay, well, it was a valiant effort. If anyone knows how to make that work, post something in the comments. But basically, so for what do we got here? This is IPRB. And this will just be P gets ingets Rosalind IPRB.txt1. And then we are putting in this thing, and that should give us our answer. Right? Theoretically. Okay, it's on disk. We just have to do the thing. Now we get a domain error. Why? Oh, because I have not parsed these as integers. Once again. Okay. Yep, those are now integers. I can do this, and I get this number, which again has like way more precision than they're expecting, but with their error bounds, this should be okay, theoretically. Yeah. Okay, and I said that if we had another integer parsing problem, that I would make a function for it. So, this can actually just be jot.not equals partition right tac, like this. And then when we are parsing, we just run int. And, oh, yeah, for each execute. Yeah, okay, perfect. And now we did something with integers down here. This thing, this can now become int. And we do int here as well. Yeah, perfect. Okay, we're over an hour. Let's look at one more and see how crazy it is. Translating RNA into protein. Ooh. Ooh. All right, let's do it real quick. we have some codons. And we're going to parse the codons. Yep. And then we're going to we're going to run this on each one of these. And then actually for each one of these, we're also going to do, I want to make a matrix out of each one. So this will be like that thing that I was doing before. This will be like divide 2, catenate 2 on the end, and then right tack row commute. Now I get a length error. Oh, well, I don't know why that one is there. Yeah, like this. Then we can get them all into a single matrix, like so. And I guess we can call this like cod for codons. And the idea is basically we have like DNA strings in the left column, and we have proteins in the right column. Yeah. Might be an easier way to do this, but whatever, it'll do. This goes in our utils. So we have cod. And then the question asks, yeah, okay. So, we can assign this to P. And then I think the idea is, oh, wait a minute. Yeah, now I have to, so if I do iota length P, because I'm pretty sure, each one of these, yeah, so we're taking segments of 3 characters of some DNA. So I can do like iota length P, and I have to subtract 1, but then I can do mod 3, 0 equals, and I can use this to partition P, like so. You might be tempted to do like a windowed reduce on P, but the problem is that this, you get overlap in the cells. So this is one of the ways where you can just partition it straight up. And then, so cod, I'm looking at the leftmost column of cod index, like so. And then we use the rightmost column of cod to index into this thing. Oh, there's a stop codon on the end, so we'll drop that. And then we just enlist mama protein string, which seems to be correct. Okay, So, okay, so we parsed our codon table. This is, the code name for this is apparently prot. And we did some can I make this train? Yes, probably. Right tack, iota dot length. Yeah. So we can just run this on, is it just the one? Yeah, it's just one string. Inget, Rosalind underscore prot.txt1. Assign that to P, and then we have this monstrosity. And fairly certain that should work. Prot exists on disk. Index error. What does P look like? What's the length of P? 2991. So you're telling me that there are DNA strings that exist. There are DNA strings that exist. Let's just make sure that this is partitioning correctly. AUG, CCA, ACG, blah, 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 blah. By the way, if I look at the last item, there's no, yeah, it didn't drop any characters or anything. So you're telling me that there are DNA sequences that exist that are not in the protein table. Or there was a stop string in there somewhere. Um, hmm. Oh. Wait, why? Oh, because I don't have to do, I did the partitioning already. Right. Yep. Okay. Good to know. Okay, I was doing the partitioning twice for some reason. So we get this string. It's pretty long. Let's see. Okay, great. What? So actually we just need to do this. And that'll do it for proteins. Okay, well, yeah, I think that's good for today. So we solved, we put together some utility functions and we solved 1, 2, 3, 4, 5, 6, 7, 8 problems. Not bad. Some of them were pretty easy, but yeah. And it's kind of, I think it's kind of fun to do these in APL. Some of the problems translate really well. Some of them you have to do quite a bit of parsing, which actually APL has like a built-in PCRE regex engine, which I almost never use. So my parsing tends to be a little more convoluted. But yeah, this is pretty good. this one can be cleaned up, I think. I really want to do that like outer product or, and then generate the vectors and filter the matrices. I'm not sure why I got a rank error on that, but hmm, well, we'll see. But yeah, that'll do it for today. Just doing some Rosalind problems. I hope that you enjoyed. Go try out some of these problems yourself. I think it's a fun site. All right. Thanks for watching, and I will catch you later.